So far, we started with sine, then we went to cosine. Cosine starts at 1. Then we did cosecant, which rides on the back of its sister function. I'd like you to draw in sine there. Just draw it in right on top of that graph for cosecant. Just to remind yourself, the cosecant rides on the back of sine. And also, there's no asymptotes that are shown on cosecant. That's bad, because you're going to have to show them on the test. So go ahead and draw in sine and then put in the asymptotes. Do the same thing for secant, because its sister function is cosine, and draw in cosine and then put in the asymptotes wherever it hits the 0. All right? Come around and make sure you got that. Okay, so then I'll have to take the time to draw them in all the way, but at least give the idea. It's an example. Here's sine. Oops. Asymptotes there and there. Okay, good enough. Now let's talk about tangent and cotangent. So tangent also has asymptotes. Would you please draw them in with me here? And I bet you can kind of tell where they are, because those lines are lining up so that they're really trying to avoid something. They're trying not to hit the asymptotes. Okay. And why would tangent have asymptotes? Remember?
Because it's sine over cosine.
And if it's sine over cosine, keep going.
So cosine cannot be 0.
Yeah, so whenever cosine would have been 0, which I'm not going to make you do this, but if I were to put in cosine, see how cosine hits 0 right there? And it would hit 0 right there. And it would hit 0 right there. And that's why it's getting asymptotes there. And there's another asymptote that's going to be here. Okay, I think you get the idea there. Now, one of the things that's key about tangent that you need to understand is this period right here is 1 pi. But then some people think, oh, it's 1 pi, so then this is pi and this is negative pi. No, then it would be 2 pi. So it's not pi and negative pi, it's pi over 2 and negative pi over 2. Half of a pi this way and half of a pi that way equals a period of 1 pi. Now that comes in a lot of places that you might not have even noticed so far. Remember how I kept on talking about the period of the other functions? All the other functions, the period was 2 pi. Now all of a sudden this one has a period of 1 pi. It gets this whole cycle done by 1 pi. It's almost like time is on the x-axis, and it's like almost like a amount of time it takes. All right. So if you're going to remember only one thing, try to remember that it looks like the x to the third graph and its asymptotes are at pi over 2 and negative pi over 2. Now, if you're going to remember a next level thing, I try to remember that, you know how all of them hit 1? It hits it exactly halfway to pi over 2. Well, that's like pi over 2 times 1/2. Do you get how that's actually pi over 4? You get what I'm saying? Halfway between 0 and pi over 2, that's where pi over 4 would be. And same thing on this next one. This is getting messy, so I'm going to erase out the green because that was just reminding us cosine, sine over cosine, and cosine hits 0. That's why we have asymptotes. Okay, so this red function has two other key spots, halfway mark right here, which would be negative pi over 4. I just tried to show you why it was a 4, because it was pi over 2, half of that. And then that's going to be negative 1. So this is 1. It's negative 1. They still have a 1 and a negative 1 in an important spot. Okay. So now you know the basics. So let's just see. I think we did good enough on the cosecant just by itself. Let's just do this one. Everybody, cosecant, which means you start with sine. Graph sine first, then do what you need to get it done so the cosecant has been moved that way. So acts like it's a test question on cosecant. I'll pause for a second. Let me finish this one off. So remember my new way of doing the numbering system that I think is better. 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. And if you like the old way, that's okay. But this, if you ever have to put a number here, which we do a lot, then you'll be able to put it on the denominator easier because they all have a denominator. So, all right, so this one has to, first of all, change from being just sine into cosecant. So do that. Asymptotes here, asymptotes here, asymptote here, and loops and loops. But now I got to move the whole thing over, and just to keep my life simple, I'm going to even move the sine graph over pi over 2. Actually, you know what? I don't need to move the sine graph. All I need to do is move everything else, including the asymptotes, of course. Think about it. If I don't move the asymptotes, the loop will end up right on top of the asymptote. So that doesn't make any sense. So I'm going to make my new graph in blue. Asymptote here. Asymptote here. Going one spot to the left. Now my loop is there. And asymptote here. And the loop goes one spot to the left. And now I can erase all the red stuff. There, I'll move to the left. And then Mr. Server would cry a little bit and mark something wrong, because whenever you move it, you gotta add some numbering. Like this is painfully missing what its name is. All of these spots are named. So we were counting by pi over 2's, right? So negative pi over 2 needed to be named. There we go. Okay, so that was cosecant, typical test of cosecant. Now tangent. See if you have any short-term memory. Just graph the middle one to start with. Okay, turn. Compare with the person next to you. Valley up. Compare with the guy behind you. All right, so looks something like that. And this is pi over 2. This is negative pi over 2. Who remembered to put in the spot in between pi over 4 and negative pi over 4? Did anybody remember to put that in there? Okay, you need to. You know why? Because if you ever vertically stretch these things, this 1 and this negative 1 would need to change. So for instance, let's say I change my problem and say 2 tangent. I got to be able to change this 1 to a 2 and this negative 1 to a negative 2. And then let's say I change this to a 5x. Would you please go ahead and do that? Change the problem to 2 tangent of 5x. All these rules we've been learning, they apply still. You know, on the inside you don't trust it. Seems like you multiply by 5, but you don't multiply by 5. All right, then instead of multiplying by 5, I multiply everything by 1/5, which I like timesing the bottom by 5. Okay, so that makes this pi over 20 and pi over 10 and negative pi over 20 and negative pi over 10. There, it's been renumbered. Now, it would be super painful to have to do -1. Where would the whole graph go if I did -1? Just say it if you know it. No, it would not go right 1. Down 1. I'll go down 1. It would be a pain, so let's not do it. I'd much more likely see us moving it to the right 1. Except not 1. I'd probably move it to the right pi over 4. Okay, so if I wanted to do that, my inside of my function would have looked like this. I'm not going to make you do it because it's so messy. But if the inside of my function had been this, you would have gone right pi over 4? Okay. So, without any help, try to graph 8 tangent of 2x. Don't worry about all this out here. Just graph it right near the origin. Once you're done with that, we'll talk about cotangent. I'll pause for a second and give this a try. Okay, so here's how you would have tackled this one. I'm not too picky on how sharp you make that turn. You could make it sharper by going like that, but I'm not going to be picky about that. Okay, next I definitely am going to be picky about this is pi over 2 and this is negative pi over 2. But then it changes and this is 1 and this is negative 1. But then it changes. This 8 makes it 8 and negative 8. And this pi over 2 and negative pi over 2, they get multiplied by 2 on the bottom. So another way to say that is you don't multiply by 2, you multiply by a half. And so then this is now 2 times 2, so this will be 4 down here and a 4 down there. How many of you guys would have had that one right? Cool. So then, how about cotangent? So cotangent, you would think it would stay in the same spot and just go the other way, which would be like this. But it doesn't. Why? Well, it's cotangent. Well, 1 over tangent. But that's not how you want to do it. Tyler? Cotangent is, try again? Cosine over sine. So if this cotangent is really cosine over sine, you may have to do this on the side of your paper later, like when you're taking the test and you're like, oh, I can't remember where the asymptotes are. You know where the asymptotes are going to be? Whenever sine hits 0. So if I make sine quick, everybody do this. Draw a sine quick. That's where it touches, those spots where it touches, that's where the asymptotes are for cotangent. So see how the asymptote's right at 0, 0, and there's an asymptote right there at pi over 2, and there's another asymptote at 2 pi. So cotangent's asymptotes, just like tangent's asymptotes, it depends on the thing that's on the bottom. All right, so now I'm going to erase out my sine graph. It just was there to tell me where to put the asymptotes. And now cotangent does go that other way. It goes down the whole time. And I want you to take a guess at this. Tangent's period was pi. What do you think cotangent's period is? Also pi. And so since this is 0, what do you think that is? Pi. So where it crosses is obviously important, and that'd be pi over 2. And then where it's halfway is important because this is the spot where you get your 1 and your negative 1. This is 1. This is negative 1. And so these two spots are important. Please label them. In between 0 and pi over 2, get used to this. Get used to cutting fractions in half. So pi over 2 is a fraction. And you want half of pi over 2. So it's pi over 4. Who had a pi over 4 there before I even said it? Good. And then I realize I'm counting by pi over 4s, and I'd go 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4, which is pi. And that feels awkward, I know, because you're used to sine and cosine. But if you start off knowing that this thing has a period of pi, that helps. All right. So this is a very reasonable, the 40 makes it seem, oh, it's crazy, but all you have to do is change 2 numbers. But that's a very reasonable test question. Everybody try, just don't do the amplitude period stuff. We'll talk about that in a minute. Just graph that for me. I know you're maybe running out of steam with your brain, but we're almost done. So good news. Just try to get this done. I just need to talk about basically one thing after that. So cotangent has asymptotes here, and they're at pi and 0, and this one's pi over 2, and then it runs like that. But then we got to change this spot to be 40, and this spot to be negative 40, and then the halfway mark, which was at pi over 4, and 3 pi over 4. And then I got to go through and multiply everything by, no, don't multiply, Mr. Server. Divide everything by pi over 2. Another way to say that is multiply everything by 2 over pi. 2 over pi. 2 over pi and 2 over pi. And the pi's would cancel. That makes this 1/2, 2 halves, 3 halves, and 4 halves. If you get used to counting like that, that makes your life much easier. So raise your hand if you feel like you'd have got that marked right on the test. Okay, good. Then There's the amplitude, the period, the horizontal shift, which is also known as the phase shift. And let's talk those through. Amplitude is super easy. The amplitude is 40. It's whatever that number is in front. But if that number in front is negative, amplitudes can't be negative. So it's the absolute value of whatever that number is. Next is the period. Always start with, well, the period's going to be pi. But then you divide by whatever you had to divide by. So divide by pi over 2 or multiply by 2 over pi. That gets me my final period. It started as pi, but this tweaked it. So its period, the pi's cancel, was just 2. Yes?
Why is the amplitude 40?
Because the number in the front is the amplitude. That's all there is to it. Okay, next up is horizontal shift. That's the phase shift. Thankfully, there wasn't anything in here. If there would have been, it would have been right there. You know, like let's say it had been pi over 2x plus pi or something. That would have been the phase shift after we factored it. But we didn't have to do any factoring here because there wasn't any number there. There wasn't any phase shift. So I'd just say none or NA. And last is vertical shift. There's no number on the outside, so also no vertical shift. Not applicable is what NA stands for. Okay. Any questions? All right. Then you have work time. Yay. Your life is pretty easy. You just need to do some practice of these. And I would do all of them on the orange page. And I feel like you're keeping up quite well with this. So I'm going to take 1 minute here to introduce the lab. Because some of you might be like, I have time tonight because this is such easy homework. I'd like to start the lab. All right, so I'm going to pause for a second. And we're going to open up the lab folder. Okay, so here's the lab. And what's it about? Well, you're going to be analyzing the number of daylight hours in a city over time. You'll be plotting data on a graph and creating a sinusoid equation to model the curve. And it's going to be worth 20 points, as it always is. It is in the summative category. So pay attention to this one. It's going to matter. So the next, it always has a purpose and a procedure and the calculation section and the graph. You got to make sure you have the labels. You always have a conclusion and reflections. Okay, every single time. We've always had labs. We've always had those. And you need this labeled like on your sheet. You got to say purpose. And the purpose is to blah, blah, blah. Okay, the only thing I have as a rule is that you have to put this in your own words because I hate the idea that kids would just copy my exact words. Okay, so you got to put it into your own words. Okay, so you could start your lab right now by just writing out what the purpose is. Just say it in your own words. And I'm going to just make sure you get the idea here. If I give you a website that tells you how much daylight there is in certain cities, okay, you'd be able to see what the longest amount of daylight is and what the shortest amount of daylight is in that city. Do you get that's kind of like this? This would be the shortest amount of daylight you ever have, and that would be the longest amount of daylight you ever have. So, would you agree that there is, at least in Minnesota, we always have a certain amount of daylight each day? And you might be like, everybody has daylight. Actually, no. There's some places up in Antarctica or down in the I get them confused, at the poles, that where you have like almost no daylight for long periods of time. Okay, we around here, we always have at least, well, maybe you'll find out how many hours of daylight we at least have. And then when it's the summertime, you guys know those glorious summer days, like in late June, where we have really long days. It can be like 9:30 at night and it's still light up. You know where the most boring places are for sunlight? I learned this because I went there. At the equator. 6 a.m. sun rises. 6 p.m. sun sets. Every single day for their whole life. Never moves. It always rises at 6 a.m., always sets at 6 p.m. Every single time. So I'm sure they like it. They're used to that. I kind of like the idea of longer days. But then again, that means you got to have shorter days too. So anyway, so we have a cycle like this, and you can write, doesn't that kind of look like the beginning of a sinusoidal equation, like, you know, a wave? So we're going to teach you how to make those. All right, so now I've introduced the lab. Not that you have much to go on yet, but at least you know that it exists. And then we're going to be writing an equation for how much daylight we have, and then we'll talk more about that on a different day. And that's all I got for you for today.